makes it doubly exciting.
Thanks, Charles. Very good introduction. So, just a technical note. Sometimes I have slides which are somewhat annoying because sometimes people change slides while you're still looking at them. And if that happens to you, you can pull up a local copy of the slides by going to brendanfodder.com and clicking this slide button down there. But anyway. Okay. So, thanks to all for that introduction. Thanks for organizing too, and for that too. And thanks for having me speak. As advertised, I'm going to speak about some ideas, sort of reflecting on the structure behind neural nets and supervised learning in general. So this talk is sort of backdrop as Fong talk. Okay, and it's sort of primarily with David, but also with Remy and Curious and Mike Johnson. Okay, so the setting is this. Supervised learning asks us to think about how to program functions like this. So there's this function, which we'll call cat question mark, from the space of pictures. Let's say they're 100 pixels by 100 pixels, and this 3 is for, say, RGB coordinates. There's another space here, which is just the free vector space on cat, not cat, as basis vectors, right? And so we all have a function in mind, because if you show me a picture of the sort, I can tell you whether it's a cat or whether it's not a cat. So this thing, it has a cat face and 4 legs and a tail, and it's a cat. So we'll map it to this basis vector cat. This here is another picture. It's a picture of Jules. Jules is probably not a cat, so we map it to probably not a cat, right? and so forth. So how do we program a function like this, right? One thing that makes it hard to program is that although this sort of function broadly exists, we all have slightly different versions of a function, of this function. So you might show me and Jules a picture, and we look at it. It's kind of blurry, and I think it's a cat, but Jules thinks it's not a cat, it's a dog, or something like that. So this function is not completely well defined, and also trying to write down some sort of closed form. I don't know, we look at the image, and like if this pixel is bright enough, then it's probably more cat-like than not. I'm trying to write down some closed form formula like that from this vector space to this vector space is not a viable way to try and get at this function. So the idea is that we have some examples here where we agree that this function is defined, and we're just going to show my phone or something like that enough examples of this, and eventually it's going to get the idea. So how does that work? So first, I'm just going to talk about this abstractly. So I'm going to define a category, which happens to be similar to the category of open games, which is very exciting, as Jules says. And then once we reflect abstractly on this notion of supervised learning, we'll see that parameterized families of functions are important. And in fact, this is where neural nets come in. So you might ask, why neural nets if you can do this all abstractly? And the reason you want neural nets is so you can actually explicitly and in sort of a finite combinatorial way write down nice classes of functions. So that's where that comes in. Then to get from this class of functions to try and some notion of learning over it, we want to talk about gradient descent and how this is implemented compositionally via backpropagation. So that's what I'm going to talk about, and then I'll close with a few short remarks on how it fits into this broad picture of systems, as Neil put yesterday, that have some sort of covariant and contravariant direction, where the covariant is some sort of material or sort of a physical or play, and the backward direction is this virtual inferential world. Okay, so supervised learning. From the example, to phrase what's going on there without any cats, the point is this. We have some sets A and B, which we think of as, say, a space of images and a space of classifications for those images. And so there's some function f that we want to find, but we only know these lists of pairs of values of the function. So some input value a and its evaluation f of a, right? And we want a general method that works regardless of what this function is from these pairs, try and figure out some approximation to f. So how are we going to do this? We're going to use this abstract structure. So the first thing we want is a hypothesis set, or I'll also say parameter space or state space, just a set of labels that will index functions from A to B. That will be our possible guess functions. So to make this, to actually realize this, we're going to have this function I, called the implementation function, which is a function from P times A to B, or carrying this A. We can also think of it as specifying a parameter. We get a function from A to B, so something like this. So we've got a class of functions to search over, and we're going to try and find f or identify f with one of these parameters. Right? But how do we do that? Well, again, we start with training pairs. So now we want to get better. We have our hypothesis, and we want to get better and get a closer approximation to f. So if you give me, if I'm running around in the state space and you give me this pair AB, what can I do? Well, I'm going to take my current hypothesis, this value sort of I at P, and I'm going to evaluate A, and I'm going to get some value in B, right? And then I'm going to compare this to this value f of A in B that you gave me. And chances are I'm going to be wrong at least slightly, right? So there are two things I can do when that happens. First, I could reflect and say, well, my choice of parameter was bad. And so given my current hypothesis and this training pair, I'm going to find a new parameter, find something that's slightly better. The other thing I can say is, it's all your fault, right? I can say, well, you gave me this picture, and you told me it's a cat, but I thought it was a dog. But if you give me a sharper picture or a better input, then I would have come closer to the correct answer. So instead of, well, as well as changing my own hypothesis, I could also give you some feedback and say, this would have been a better picture to give me. Right? So this data here we call altogether a learner. More properly, I mean, Dan raised size issues yesterday, and so maybe we should consider this hypothesis set P as just a subset of these functions. Maybe we shouldn't. But to get around size issues and to make the categorical composition associative on the nose, we're going to take equivalence classes where we kind of just do the obvious thing. It's the weakest notion of equivalence class. That makes sense. Right, so I guess I just spoiled the fact that these things form a category. But before I go there, let me make, since this is an open games workshop, maybe this will help orient you with respect to this data. So there's a rough analogy, which we'll come back to briefly, but to help orient you, we think of P as somewhat like the set of strategies. The implementation function has exactly the same type as this play function. Here, so open games have these sort of state and co-utility as input, and move and utility as output. Here we just have a single input A and a single output B. So, but you can sort of identify those sort of two inputs and those two outputs. And if you do that, the co-utility function has exactly the same form as the request function. But in spirit also they're the same. They're about feeding back some sort of virtual information. The update function then is left to be somewhat like the equilibrium function or the best response function. And that's true, but you have to squint slightly. And perhaps we'll explore that more in the discussion time. OK, but for now, this thing is a learner. And this is a compositional framework for supervised learning because we can compose these learners. We have a symmetric monodal category learn, where the objects are sets and the morphisms are these learners. Okay. So I've told you we have a category. You should ask, what is composition in this category? How does it work? The key idea here is that composition is about creating local training data. So the point is, I have two learners. One learns functions from A to B, and another learns functions from B to C, and I want to learn a function from A to C. But my training pairs for learning functions from A to C is an element of A with an element of C. Right? So how do I reduce that to get the AB pair and the BC pair that help can train these individual learners? Right? So to get a sense of an example why you might want to do this, you could think of this as a space of images and this as a space of cat, not cat labels as before. And we think of it as factored into via some sort of feature space. So B is a space that sort of identifies, I don't know, whether it has a face, whether it has eyes, how many legs it has, and so on. And so so it's definitely possible that there exists a function from images to just what you see in those images. And then you might have a function from these features that says, well, if it has 4 legs, it's more likely to be a cat. If it has 3 legs, well, it's an image, and one of them might be occluded, or one of them just might be missing. So it's still a cat. But if it doesn't have a head, then it's probably not a cat. So such functions exist. Anyway, OK. So to compose these two learners more abstractly, we've got to construct a new parameter space. The new parameter space is just the product of these individual parameter spaces. So every degree of freedom we have for these individual learners is a degree of freedom in the composite. To talk about the implementation function and the update and request functions, it's a tiny bit more complicated. And to give you an idea of what's going on quickly, I'm going to use some string diagrams. So these are string diagrams in the category of sets. This represents a function I from P times A to B. I paired you'll notice that the update and request function have the same domain. So we can pair them to be a function from P times A times B to P times A. OK, so the key idea here is that we can just really follow our nose. We want to produce we have the types of the composite data, and we've got some pieces which we can assemble things of that type, and we do really the only thing we can. So a very simple example of this is the implementation function. Here we have, we're looking for a function Q times P times A to C. And so we have these values QPA, and we want to get a value of C. How do we get a value of C? Well, we've got this function J, which spits out values of C. But and in fact, J takes in a Q and a B. We've luckily got a Q here, so we just plot that right in. But we need to produce a value of B. But how do we produce values of B? Well, I spits out values of B. So we can put that there, but now we need a P and an A, but we've got a P and an A. So the composite is just precisely that. Another way of thinking about this is that once we fix parameter values, then I at P is a function from A to B, and J at Q is a function from B to C. And this is just the composite of those two functions. So this is obvious, and especially if you've seen the same thing happen with open games. Composing update and request functions is a bit more complicated, but it is, you play the same game you do with open games. So here's it in string diagram form. Here's some messy equation that expresses exactly the same thing. But just so we're reading this correctly, say we want to know what this value of P that is spit out here is. Well, this is this value here, this sort of this middle element of this tuple. So this is a box that sort of is the update function and the request function. So it's spitting out the update of the function U of these three inputs. These two values come directly from the P and A that have been input. This value here is comes out of the second output of this box, which is S. Right? So it's S of something. That thing is, again, we take that Q and the C from the input, and then we put in this I of, again, PA. So it's hard to read, but if you stare at it long enough, you'll see that it's the really only sensible thing, given this data. The question you might have then is, how do you come up with this data? And now that I've made this notion quite opaque, let's try and think about the intuition a bit more. So this is the same diagram. But what does this diagram mean? Well, again, let's think about what's going on. We have these learners with implementation functions I and j, and we have hypotheses p and q. And we're presented with this training pair AC. And now we want to be able to update these parameters p to p prime and q to q prime using this update function, the respective update functions u and v. So we need to produce an AB pair and a BC pair. How do we do that? Well, as it stands, we have one good way of producing Bs. Right? We've got an A, and then we've got this hypothesized function from A to B. So we can just bang that A through and get this value of B, I of P comma A. So now we have this pair BC, and that works well for updating this. But this value B is not a good value for trying to update this, this first learner. Why is that? Well, if we just use that value B, this value is I at P comma A, right? So so it's exactly the value spit out by hypothesis. So if we tried to learn with respect to this value, we'd find that we're already always correct. And this thing is perfect and doesn't need to learn anything. So anything upstream would not be updated. But again, this thing is not perfect. And there is the chance that it could have done better at spitting out a value for this thing to learn. And so this is where the request function comes in, and why this sort of slightly subtle bit of structure is necessary for a compositional way to think about supervised learning. So this learner here spits out with these parameter values, spits out through the request function, which is called S for this learner, this other value of B. And this forms the training pair for this first learner. Right? So now that we have an AB pair and a BC pair, we can apply the respective update functions, U and V, to get these new parameters. And so this intuition is exactly what's expressed in this diagram. OK, so we have, I guess I said we had a monoidal category, a symmetric monoidal category. And I won't tell you much more about the data. But just so it's clear, the monoidal product is fairly straightforward. It's taking the Cartesian product across the board. So the new state space is P times Q, and the new implementation function is the product of the implementation function, and so on for the request and update functions. And you'll have to believe me that this is a symmetric monoidal category. OK, so we've got a compositional framework for supervised learning. It's a framework for learning because we can update parameters. It's supervised because we tell the learning agent the correct answers, right? We give it inputs together with the correct output as pairs. And it's compositional because we have this symmetric monoidal structure, which allows us to build new learners from old. Right? So this is great. We have a world where we can write down learning algorithms, except for the fact that we don't have any algorithms yet. We don't have an explicit way to define an interesting notion, an interesting morphism in this category. So the question is, how can we explicitly construct a learner? So this is where neural nets come in. And the idea here is that instead of looking at all the data, let's just look at the first bit. Let's look at, a fortiori, to specify a learner, you need to first start by specifying a state space, and then that state space, a class of functions, or functions parametrized by that state space, this implementation function. So let's start by thinking of ways to specify these things. And again, neural nets are a way to specify such a thing. So part 2, specifying parameterized functions. So here's a new symmetric monoidal category. In particular, it's a prop. So the objects are natural numbers. And so for those who are not familiar with this term, a prop is a strict symmetric monoidal category where the objects are natural numbers and the monodal product is given by addition on objects. So in particular, it's tautological that the prop para has objects natural numbers. But I want to define this prop where we think of these natural numbers as defining the dimensions of Euclidean spaces or vector spaces, if you like. And the morphisms then are differentiable sort of functions that are parametrized by some other Euclidean space. So this plays the role of P. In particular, it's R to the K now. And also that this is done in a differentiable way. So we'll see that this differentiability is quite important and is a conceptual advance in the theory of machine learning, although from the 60s or so, I think. But as we saw for the category learn, this sort of parametrized function has a natural notion of composition. And so this here is a very sort of simple symmetric monodal category. OK. So the key idea here is that neural networks are some compositional combinatorial language for specifying these differentiably parametrized functions. So what is a neural network? For the simple purposes of this talk, I'm just going to think of them as sequences of bipartite graphs. So here's a sequence, firstly, of natural numbers, 2, 2, 1. And then for each consecutive pair of natural numbers, I can put a simple undirected bipartite graph between them. That is the connections, which we think of as connections between these nodes, which we think of as sort of virtual neurons or neurologically inspired. So this is a very nice bit of combinatorial data. For example, I can just give you a sequence of natural numbers, 1 million, 1 million, 1 million, 100, and say, put the complete bipartite graphs between them, and you've got some structure. And I claim that structure indexes a parametrized function. So what does it index? What function do we get? Firstly, we need to specify this thing known as the activation function. And once we've done that, we get the parametrized function. The function runs from, again, we have a first layer, which is going to have, say, in this case, 2 nodes. So it runs from the vector space of dimension, the number of inputs, to the vector space of dimension, the number of outputs. So in particular, this is a parametrized function from 2 to 1. The parameter space is constructed as follows. We get a parameter for each edge and a parameter for each node that's not an input node. And I've split the parameters up. This is sort of thought of as a composite of this first layer and the second layer. So in the first layer, we have 5 parameters. We have 3 edges and 2 nodes. So this is this R to the 5 here. In the second layer, we have 2 edges and 1 node. So we have this R to the 3 here. The parameters associated with the edges are called weights, and the parameters associated with the nodes are called biases. OK. Now, but what function do we get? The basic idea is this. If we put in, we start with some inputs at the input nodes, some value A1 here and some value A2 here. And we feed forward by, we have weights on these edges. We take a weighted sum according to these weights of these inputs, then add the bias associated to this node, and then we get some weighted sum here. This is precisely this thing here. So P11 is the value associated with this edge from 1 to 1. P12 is this the weight associated with this edge from 2 to 1. So we take a weighted sum of A1 and A2, and then we add this bias. This is the bias of the first node. Then we apply this activation function, and we can just sort of propagate this through. So we do that here, we do that again here, getting this value here, A1 times the weight plus the bias associated with the second node, apply the activation function, and then we get 2 values here and here, and then we do the same thing using those 2 values for this neuron. So Q1 is the weight associated with this, and Q2 is the weight here. So we take the weighted sum of these two values, add the bias associated with here, and apply sigma. All right. So that's the rough idea. Well, that's the idea in this particular example. A couple of words on activation function. So why is it called an activation function? The idea is that this function, so classically, we used sort of sigma as a step function. And the idea here would be that if this value is, after we evaluate it, greater than 0, then we think of it returns 1. So we think of the neuron as firing. But if it doesn't make this threshold, then it's going to be negative, and the neuron just returns nothing. It doesn't fire, right? The problem you'll notice with this is that it's not differentiable. So one common choice of activation function is anything like an arctan or something that is just some smooth approximation of a step function. But while differentiability is important, it's also important for speed reasons. And so the other thing that people like to use is something that has a really easy derivative to compute. So one thing that has a very easy derivative to compute is flat until 0 and then constant up. And it's undefined here, but in practice, it's point to measure 0, and it doesn't really affect computation. So this is about the simplest thing you have to differentiate. And so this is often used as a value of sigma. In the end, what matters most is that it just throws in some nonlinearity to this linear process, right? If we just make this identity, then this is just matrix multiplication. It's precisely graphical linear algebra.
So you only need it to be differentiable once?
Yes, we only need it to be differentiable once. OK, but it so happens that when you throw in this one nonlinear function and compose with it, then you actually get a wide class of functions that's, if you pick your net well enough, capable of approximating anything that you come up with. OK, so I said this is a compositional language for specifying differentiable parameterized functions. The combinatorialness is just the finiteness of the structure. What do I mean by compositional? Well, I mean there's a functor. So I define this prop where the objects are, again, natural numbers. The morphisms are this notion of neural network, which are just sequences of bipartite graphs. And composition is just the free thing. We just glom them together. Right? So here's a prop where morphisms are just the pictures you can draw on the previous slide. And then the theorem is that once you pick a differentiable function sigma, so an activation function, then we have a prop function which I've called I sub sigma, I for implementation with the activation function sigma, from this prop of neural nets to the prop of parametrized functions. So in particular, a prop functor is identity on objects and strict symmetric monodal. And so here we have, I think, the expression of why neural networks are so useful to us. They give us a way of, a very compact way, but also a compositional way of specifying what we're really after for machine learning, which is classes of functions to search over. Martha? So yes, for this to be a functor, it does. But that, and that's exactly what I want to talk about next, right? So I may have presented a quite naive version of what neural networks are, which I argue captures the sort of basic ideas. But there are all sorts of things you can do to vary what's going on. So we can vary this differentiable function across the network. We can also try and do things like identify weights. And that's one, crucial to notions of convolutional neural network and recurrent neural network, which are very, very widely applied. But they're not so, they're sort of superstructural on this idea of a neural network. You draw your network, and then you say in some other syntax, we want to identify this variable and this variable, or we want to choose different activation functions here and here. But what I argue is important is just trying to find a class of morphism here that's, for training reasons, as we'll see later, differentiable. So let's just think about the category para for a bit. And the point I want to make is that differentiable parameterized functions can also be constructed using string diagrams in para. And para has a lot of nice, interesting structure. So to begin, every object in para is sort of canonically equipped with the structure of a bimonoid. And if you don't know what that is, I'll say things more explicitly. But Pavel's in the audience, and wherever Pavel goes, graphical linear algebra goes too. So I want to make some comments inspired by that. So we have this prop para. Now, if we think inside para of the differentiable functions that aren't actually parametrized, right, that have a trivial parameterization space, this is still a nice subcategory, and it's just the subcategory of differentiable functions between Euclidean spaces sitting inside para. So there's a nice prop inclusion, as nice as you like there. But then maps between linear maps are differentiable. So the prop of finite dimensional vector spaces and matrices or linear maps between them sits inside here. So we have f(vect) sitting inside para. And since every object here is equipped with a canonical bimonoid, which is given with the multiplication given by addition and the co-multiplication given by copying, this structure is transferred to para. So one thing this allows us to do is if we define these sort of primitives here. So now these are, before I was drawing string diagrams in set, now I'm drawing string diagrams in para. And I'm going to pull out these two canonical morphisms and just give them this syntactic sugar. And we know from Pavel's work that these obey really nice laws, which we think of as sort of networky. So here are two generators. As we've seen, sigma just is a differentiable function, so there's this realization of it as a parameterized function with trivial zero-dimensional state space. So that's a morphism in para. And if I want to throw in sort of the simplest other morphisms in para that I can think of, I might pick, say, these two generators, where we have no input and a one-dimensional state space. And what this morphism does is it's just going to spit out the state, right? So, and this thing with a zero-dimensional space here and a one-dimensional space here precisely represents a function from R to R, and we're just going to pick the identity function. And then I'm going to pick this generator here, which has a notion of state and a notion of input, but it's just going to be scalar multiplication or weighting, right? So I'm looking at a function from R times R to R, and that function is just going to have some stored value W, and it's going to take the input and multiply that by W. Right, so here's another parameterized function. So I'm playing this game in para where I'm just pulling out some morphisms that are very simple, so I can use them to generate string diagrams, to generate some subcategory of subsymmetric monodal category of para. And as we'll see, I can use this language to specify learners in a second. But what's interesting is that another nice fact about neural networks is that about this language is strong enough to generate all neural networks. So every neural network is precisely implemented by these generators where, well, we do the sort of natural, we just talk through my description of neural nets, right? So what happens with a neural net is we have a bunch of, at each individual neuron, we have a bunch of inputs. We multiply by the stored weights. We pull out this bias. We add them all together. We shove them through the activation function, and then we copy them out to all other neurons that take that as input. Right? So a neural network is the image of the category NNet lies in this space, lies in the subprop generated by these things. But this subprop is bigger in that we can express things that can't natively be expressed in the language of neural nets. So one thing is weight tying. So another nice structure that the category para has is that what is a morphism? It's a state space together with an implementation function, and we can always factorize these out. So we can factorize this thing out with sort of a trivial implementation function, so it's just sort of a walking state space. And then here we have no state space, and it's just this differentiable function. Right? And it's not too difficult to check that we always have this identity. So given two morphisms with the same state space, R to the k, let's call them I and j, we might want to say that actually these two things should be considered, that the parameters that they work off should be considered the same. So an example of this comes from the application of our convolutional neural nets to computer vision. And the idea is essentially that if we have an image, all the structure of an image, well, much of the structure of an image is local, right? So like an eye, if you want to check whether the image has an eye in it, you only need to search sort of sub-areas that are, say, I don't know, let's say 100 pixels by 100 pixels or whatever. So we can construct these neural nets where we scan over the image in these small areas looking for structure. Or you might, instead of an eye, you would often consider looking for edges or certain textures, things more basic. But even though we're sort of scanning it over with different units, so we have different maps. We have one neuron here that takes in this square as input, and a neuron over here that takes in this square as input, and so on. That we want them to, the structure that it's looking for is invariant over the image. So we want to say that these things are all recognizing the same structure. And so to do that, we tie the weights together. So again, that's some sort of superstructure you put on neural networks, but it's expressed natively precisely by this copying generator, right? We pull out the state spaces, and then we just say we have the single state space, and it's going to spit out a value, and it's going to get copied to these two other learners. So then the point here is that Para is a more powerful language for expressing these classes of differentiably parameterized functions. And so somebody vaguely made a remark about software yesterday, so to opportunistically jump onto that, I think it'd be really cool just to write up some library that allows you to pick a few very basic generators, draw things using string diagrams or some way of generating string diagrams, and then it compiles to a class of parameterized functions and feeds it to TensorFlow or something, and just to play around. In some sense, it can't be more powerful than neural nets because neural nets have a known generality theorem, but then a universality theorem. But then that theorem is not actually that interesting in that it says that all the structure can be obtained by sort of one layer, a wide enough one-layer neural network. And the interesting questions in neural networks seem to come from not whether you can find a class that has some approximation to the function that you want, but what a good way to do that is. And so this broadens this sort of collection of ways you can still quite easily define classes of parameterized functions. OK, but I've got about 15 minutes left, and I haven't actually talked about backpropagation or learning. So let me do that now. This section is short. The key idea is that we want to, from parameterized functions, we want to create an update function and a request function using gradient descent, and that backprop is precisely an expression of the functoriality of this process. So here's a theorem with a lot of notation. But it's the same flavor as this previous functor from neural nets to Para. So we're going to fix some data. Before we had to fix an activation function. Now we fix this epsilon greater than 0, which we think of as a step size or a learning rate. And we also fix this e, which takes in two real numbers and spits out a third. And this e we think of as an error function that basically just says, here are two numbers, how bad is the difference between them? It has this technical condition that if we differentiate with respect to the first variable and fix some value, then that's an invertible function. So once we have these 2 bits of data, we get a very nice monoidal functor from Para2Learn. It's faithful injective on objects and a strong symmetric monoidal functor. What does this functor do? Well, it takes each parametrized function and, again, constructs this update function and this request function. And it does it by differentiation. So I'm going to write this capital E sub I for just the sum of the coordinate-wise errors between our hypothesized value, our hypothesized output, and the true value. Right? So this is just some net error function. And if we take the gradient of that with respect to the parameter space P, we're just going to update by taking our parameter and moving 1 step size in that gradient. The request function is essentially the same idea, but of course we have to do it with respect to the input A. So again, we take the same error function, but now we compute the gradient with respect to A. And then this inverse here is, again, what we want to feed back is not the gradient, but the request for the better value, the slightly sharper image, or something like that. So we have to put it through this inverse. So this is better understood in a particular example. So here's an example of a common error function. It's called the quadratic error, and we just take the difference between 2 values, square it, and I've thrown in a half for good measure, because I like throwing in halves after I square things. So what this theorem says in this case is that for every step size, there's a really nice functor. I've left out some of the conditions from Para2Learn that for which there's an update function and request function defined coordinate-wise as follows. So how do we update each coordinate of each individual parameter? Well, this here is just the gradient times the difference between the dot product of the gradient with the difference between our guess and the true value. Right? So we just take that dot product and then subtract an epsilon multiple of that. And then for the request function, again, this is just the gradient in A times the difference, our error, and we move a whole step in that direction. So in particular, the epsilon is missing here. But that's the general idea. So again, it's just we have this, and since we know our parameterized function is differentiable, we can construct this update and request function using derivatives, using gradient descent. OK, but what does this theorem mean? So the key idea is this. Imagine some large neural net, which can have sort of millions or literally millions and millions of neurons, of nodes. Now, if we want to compute over this, we can isolate. So what we could do is we could compose this and get this giant function in millions and millions of parameters and try and differentiate that. And that would give us a good notion of gradient descent because we know we're descending with respect to some error function that we understood well. But computing the derivative of such a large thing is computationally really intensive. The other thing we can do is consider this as factored into individual pieces, individual neurons. And we can also just think about doing gradient descent with respect to each of these, in each of these units. And then we only have to consider sort of gradient descent or differentiation in functions the size of the integree of each node. So especially if we do something like a convolutional neural net, it's often much, much smaller. But we can take these individual units, map them into learn, and then construct some sort of composite learner using these request functions, so by passing messages around. So these things are much more computationally efficient, and this message passing isn't so bad. But what we know from the functoriality is this computes exactly the same thing as if we tried this expensive process of trying to differentiate over the entire network at once. So that sort of beyond this advance to think about differentiable activation functions, perhaps the second major conceptual advance since perceptrons in the theory of neural networks is this way of factoring this gradient descent and making the distributed a thing. So note also, though, that this isn't intrinsic to machine learning. We just to neural nets. We just started at para. So in this way of building classes of parametrized functions using string diagrams in para or using composition in para, we still have a canonical. We specify it not only a thing to search over, but also a canonical way of dividing it into sort of efficient parts. Right? So we specify an actual algorithm that is much more efficient than just pulling that class of functions out of nowhere. OK, so I won't dwell too long on this slide, but here's an image that David likes, that David Spivak, that just sort of summarizes all these buzzwords or sort of technical terms you see associated with the machine learning and sort of identifies them at different points in the structure. So I don't know, the activation function is something that allows you to take a neural net and turn it into a parameterized function. But actual back propagation is something that happens over here in this structure where we learn. It's on the internet if you want to keep looking at that. But in the last 5 minutes, just a few words about how this relates to the topic of the workshop. So there's a strong analogy between learners and lenses. And so for those of you that don't know what a lens is, here's a one-line definition. A lens is a learner with a trivial state space. What does this mean? Well, it means that this space is trivial, right? It's a one-dimensional space. So this means that when we look at the implementation function, we have nothing here, so we just have a function from the input to the output. And this is known as put in the world of asymmetric lenses. The update function is trivial because it goes to the terminal, some terminal object. And the request function is now just a function from A times B to A. And this is known as the get. So there is some obvious inclusion functor from the category of asymmetric lenses into the category of learners. But they're more strongly related than that, in that there's also a map from learners to not asymmetric lenses, but something that lives in that world, this world of database theory or bidirectional transformations. And the map is this. So a span is just a map is a pair of maps with a common domain. So we think of this is the common domain of this map and this map, and we think of it as a map from A to B. Right? And so we can encode the data of a learner in the data of a span of asymmetric lenses in a really nice sort of efficient way, but also in a compositional way. So the theorem says that there's a nice functor from the category learn to the category of spans of asymmetric lenses, where I won't tell you what the composition rule is, but it is preserved. And what does this do? It maps a learner to this span. So let's try and read this. We have a lens from asymmetric lens from P times A to A. What does this mean? It means we have a put function from P times A to A. We're just going to project out the A value. And we have a get function from P times A to P times A. Right? So what are we going to do for that? We're going to extract the P, and then we're going to use just the second value of A. So this is a simple canonical thing. But it's the other leg that encodes the data of the learner. So the learner is going to be seen as an asymmetric lens from P times A to B. So what is this? Well, the put function is a map p times a to b. This is exactly the type of the implementation function, and we'll just use that. The get function is going to be a map from p times a times b to p times a. But that's exactly the function of this pairing, the type of the pairing of the update and request function. So we'll just pair them, and that gives us an asymmetric lens. So this is clearly something you can do, and the miracle is that it's functorial. Okay. It doesn't. But it has pullbacks when one leg is nice enough, and this leg happens to be nice enough and be preserved. Yeah, there's something tricky to be aware, to just take care of. Yeah, it doesn't have pullbacks, but it still has a composition rule, is the point. Okay. This is the last slide, and I just wanted to throw up this analogy in a bit more detail. So again, these learners and these open games have this sort of similar flavor, in particular with this sort of request function and this co-utility function, which seems to have sort of surprised the originators of both structures. But the analogy more precisely is this then. A learner goes from A to B. An open game has a pair of input spaces and output spaces. Then hypotheses map nicely onto strategy profiles. The usual notation uses different orderings, but they're fine. So P plays the role of sigma, A plays the role of X, and B plays the role of Y. So that's a direct analogy. Down to request, you'll see that while A corresponds to X, you have to sort of use these utility and co-utility spaces for these things. So it sort of expands out the structure in this way. And then we have this update function here, which I won't talk through, but you can stare at it. And I'll leave you to stare at it while I take questions, I guess. Thanks. Of your I said your decomposition. So the idea was to be a bit more combinatorial and to start with some generators that you like in the category parametrize function, and then build up some large function. Then you can map that through to this category learn. But you have this functoriality which says that mapping through as a whole was the same as mapping through these individual pieces. And then this notion of composition and learn is precisely an algorithm for computing this derivative of the whole thing just by message passing between these generators that you constructed your algorithm from.
Okay, so the idea is that you actually know how the big thing was constructed already.
Yeah.
Okay,
so it doesn't come for free, yeah. But the process of using generators to specify one of these structures knows this decomposition, and so knows this algorithm.
But if you now think of assessing where you have a machine learning algorithm, you know what the big thing is.
Yeah.
Do you have ways of finding a good decomposition using a framework?
I have no.
I don't know. Yeah, I mean,
I'm not sure how that. Yeah.
I guess.
Yeah, so you'd want some sort of factoring theorem for parameterized functions. It seems like that's a very general question.
Yeah,
these are the really kind of interesting semantic questions.
Yeah, no, it's a good question. Yeah, this I think is a great question in this entire field, right? We have these great languages for talking about building structures up, but there are not that many theorems that say, here are good factorizations of a structure in this language that were created. I think it's a great question.
Isn't it related to principal component analysis? So So that's structuring the output.
Uh-huh.
But there is also so-called active subspace decomposition, which is structuring the inputs. I think this is actually
But
what you are asking for.
But PCA is with respect to a linear function. And
Yeah, sure, that's the basic thing.
right, and so the interesting part here is that we can approximate all functions, no matter how badly behaved they are. Yeah, so there are, I guess in special enough cases, there are very good methods to do this, and this was what makes something like linear algebra so powerful.
Can you go to the previous slide, please?
Sure.
So it's probably a naive question, but like asymmetric lens, you define it as a learner with trivial state space. So if I come from like Haskell background, right, and I use one lenses, what would be non-trivial lenses if I parametrize them by parameters? Is there any meaningful intuition that I can build about this?
I don't know, I'm not familiar. So this definition comes out of the bidirectional transformations community. And this is the basic notion of lens they use. And I know Haskell uses, as I asked Jules yesterday,
Haskell uses four-legged lenses.
yeah, which are apparently something that's almost similar, almost the same.
Almost the same
but
as in open games.
right, but slightly different. And I'm not familiar enough with the details, but if you tell me more about Haskell lenses, I'd be very happy to think more about it.
Generalize the B, maybe on the left and the right, into four, so you get four types.
Mm-hmm.
Yeah.
So now B and B are the same, but you could have A to B, and then I guess A to C to B.
Yeah, but we already have that in Haskell, right?
Yes,
Right.
but this is subtle because the usefulness of this in Haskell relies on you have a polymorphic type system.
Right.
Whereas in open games you work on a set. So it's kind of polymorphic. So they're usually called polymorphic lenses, and then you take away the polymorphism.
Okay.
Cool.
Okay, so we move to discussion. So I guess a good starting point would be your next slide. So thank you for starting the discussion. So can everyone see how this relates? So there is a functor. There is a functor from the category of learners to the category of open games, which on objects takes the set A to the pair AA.
Right.
Right. So that makes the request and co-utility match up exactly. The tricky one is updates and equilibrium. So